So I finished my general announcements and I shared this video on YouTube, and it comes with a purpose. Okay. My opinion is if somebody comes up to you with their phone and they say to you, "Oh, you got to look at this. It's so cute." You instantly have, through your life experience, an expectation. You have an internal definition of what you consider to be cute. And when they show you the video, you can have, in my opinion, one of three reactions. And these can be, of course, they're one of three categorical reactions. One is you don't find it cute at all. You're just like, I don't know what the heck you're talking about. That thing is not cute. So compared to the things in your life you consider cute, it fails miserably. Okay. Or you might react to it and be like, oh, yeah, that's kind of cute. And it's just sort of what you would expect from something that is cute. Does that make sense? Or it blows you away and it truly is like the cutest thing you've ever seen in your life. You're like, oh my God, it's cute. Okay. And this is, by the way, to connect to something else, this is why, in my opinion, it is so unbelievably easy to impress little kids because their bank of life experiences is tiny. So it's so much easier to impress them because they have so little experience to draw on. Okay. So they're really excited by the, forgive me for saying it, the dumbest things. I mean, what grown people might think are kind of silly things. So you all clearly vote for the baby, and what I would say is it may not have even been super impressive to you. It's possible the baby was underwhelming, that you were just like, yeah, that's kind of cool. It's possible you weren't even impressed. But the degree to which you were impressed is more than how cute the puppy was on a cute scale or how embarrassing the cat was on an embarrassing scale. Does that make sense? All it really means is that wherever the baby was, it was higher on its respective curve compared to the others. Now, it's also possible that a lot of you were just like, oh my gosh, that's so amazing. It's so cute. And you just weren't impressed by the puppy and the cat. But it's also possible there's somebody in this room that voted for the baby, not because the others weren't impressive. Like they were like, oh yeah, that is really cute. And oh my gosh, that is really embarrassing. And then they were like, oh, that's cute. You see what I'm fact that more than 2/3 of the class voted for me means we clearly feel like on their respective scales of cute, win, and fail, the baby was the most impressive. Does that make sense? Okay. Obviously, some of you disagree, but what I would argue is for those of you, because we had a few people vote for the cat, what I would say is for those people, yeah, the baby may have been cool, level to which the cat was embarrassing, okay, or how deserving it was of winning overall was high within its scale. So not for everybody, but for most of you, the baby was the most impressive. Okay. And that is sort of what a normal curve is all about. It allows you to compare things that are not directly comparable because you analyze them within their population. So with that in mind, I'm going to walk you through 2.118, and I'm going to ask you all to do a problem yourselves, and we're going to do that again one more time today. Okay, there will be one very important new skill that I teach you today. It's not going to start off that way. The first two problems we do today should feel like review, should feel like, yeah, I already know how to do this. But then we'll change gears and look at something we haven't seen before. All right, so again, make sure you're on 2.118. True story, Mr. Oben's second son, Gavin, was born prematurely on August 28th, 2014 at 4 pounds, 9 ounces. Actually, all three of my kids were born premature. Dominic, and Gavin wasn't even the smallest. Dominic got down to 3 pounds, 2 ounces. So Gavin was actually kind of the middle in the weights. Amelia was the biggest, and not by much. She was 5 pounds and a few ounces. In any case, use the normal curve for birth weights of full-term babies to answer the questions that follow. And what I'm hoping you all now start to realize is that that one little piece of notation is shape, center, and spread packed into one. It's a normally distributed curve centered on 7.6 pounds with a standard deviation of 1.3. So what that's telling you, if it really is accurate, is if you add and subtract 1.3 to 7.6 in order to get the interval 6.3 to 8.9, according to that interval, you've just captured about 68% of full-term babies. Make sense? Okay, that's the power of a normal curve. Now, it says note there's 16 ounces in a pound. This is because we will have to convert my son's weight of 4 pounds, 9 ounces. A lot of people make the mistake of thinking that 4 pounds, 9 ounces is 4.9 pounds. It is not. 8 ounces is half a pound. So if you're 4 pounds, 8 ounces, you're 4.5 pounds. So the fact that he was 4 pounds, 9 ounces means he's a little bit more than 4.5 pounds. Let's make sure that that makes sense. Okay. Now, the question says, what percent of full-term babies are born as small or smaller than Gavin? In other words, we're going to want to find 4 pounds, 9 ounces on this curve, which is somewhere around there. And we want to find the percent of babies that are as small or smaller than him. You can do this if you know about normal curves and you know how to find a z-score, and you either know how to use the pink paper or you know how to use a graphing calculator. And I would continue to argue you really should know how to use both. Okay, they both have their own respective strengths. Calculator is efficient. Pink paper enforces just a basic understanding of what the heck is going on. Okay, so you start by how far from expected are you in pounds? So what is your weight minus the mean weight? And I now know how many pounds below expected you are, but that is not a z-score. A z-score represents the number of standard deviations you are from the mean, which is why we divide this by our standard deviation. Now you can see in the picture, clearly he is more than 2 standard deviations below expected. Okay, so I'm expecting a negative 2 point something number here. Negative 2.337. Now, if you're going to use the z-chart to convert that to a percentile, okay, remember, a percentile is nothing more than what percent of the population is under you, okay? Then all you have to do is look up that z-score on your pink paper. Now, remember, the pink paper is limited to decimal places, so I can't look up negative 2.337, but I'll go ahead and round it, call it 2.34, okay? So I go to my pink paper, which I thought I had ready to go. Yes, there we go. And I'm going to find negative 2.34. Negative 2.3, not 30, not 31, not 32, not 33, but 34. And it looks like less than 1% of babies are born under that weight, 0.96%, or as a decimal, 0.0096. Okay? And of course, you could have used the normal CDF command and just say, well, start on the normal command, go all the way to the left and shade, 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 shade until you get to this z-score of negative 2 point, hey, come back, of negative 2.337. Questions so far? Okay, so this shouldn't feel new. This should feel like if I had told you to do this problem, you could. Okay, with the one exception of, I think a lot of people are going to trip up on this and they'll accidentally put 4.9 here, which would be wrong. The nice thing is 4.9 is almost in the exact same location. Okay, so it doesn't really change a whole lot other than your z-score and your percentage. And by the way, if you follow through with that mistake, you'd still get all the credit except for 1 point. Okay, if all you did was mess up the conversion from weight to pounds, of 4 pounds, 9 ounces to actual pounds, well, that's technically speaking one mistake. So your z-score is going to be wrong, your percentage is going to be wrong, and yet you're going to get full credit for both, assuming you show work. Okay. Next question says, when using a normal model, all values at least 2 standard deviations from expected are considered outliers, given that, according to this model, was Gavin unusually small at birth? And all you have to say is yes, and give some kind of justification. And that can be based on the picture. He's more than 2 standard deviations below the mean. Or that could be comparing his z-score to a z-score of negative 2. I said, yes, he is more than 2 standard deviations below the expected birth weight. Okay, or you could say, yes, z-score of negative 2.337 is less than negative 2. Okay. All right. Is it appropriate to use this model to assess Gavin's birth weight? I'll ruin the punchline a little bit and say no, but more importantly, I'm wondering if anyone can explain why it is ridiculous to look at this model and say, yep, he's unusually small. It's because he was born premature. You got it. In the very beginning of the problem, it says Gavin was born prematurely. And then it goes on to say, here's a normal curve to talk about full-term babies. That makes absolutely no sense. And by the way, I created this problem from personal experience. And I want to be clear, I was not upset with a doctor at any point. I was not upset with a nurse at any point, but I felt motivated to educate them on how bad what they were doing was how bad it was to do this to people who don't understand statistics. Let me quickly explain. As I said, all 3 of our kids were born premature. Okay, and our first son was the most so. He was in the NICU, the neonatal intensive care unit, for the first month of his life. Okay, and his life was very much in question. Okay, So you're already in a state of like you're stressed out, you're worried about your kid, you don't know if they're going to be okay. And what we would have is constantly, every time a doctor or a nurse came up to us to talk to us for that day, there was sort of a routine that they clearly went through where they talked about basic vitals and percentiles. And over and over and over again, they would say things to us like, he's at the second percentile for height and the third percentile for weight and the fourth percentile for this and the third percentile for that. And they'd rattle off all these percentiles talking about how low he was. And I would very calmly say to them, just out of curiosity, our son, was born about 2 months early. These percentiles you're giving us, is that comparing him to other premature babies? And the problem is, and they all kind of give the same response, there are not models based on prematurity because prematurity is on a crazy variable scale. It's like, were you 1 week early? Were you 2 weeks early? Were you 3 weeks early? And they don't have the data, and the percentiles they report are relative to full-term babies. Okay. So it makes perfect sense that my son would be at the third percentile for everything because the babies he's being compared to had 2 extra months to grow before being born. Does that make sense? But it's possible, hear me on this, it's possible that within the population of all babies born equally early, of all babies born 2 months early, that he's actually right where they are, that he's at like the 50th percentile. Does that make sense? So it's very possible that relative to his population, he's a totally healthy, normal baby. Does that make sense? And yet you're reporting to me that he's the third percentile in everything. So I would basically calmly explain this and just say, do you understand that the percentiles you're giving me mean literally nothing to me? Because you yourself told me it's percentiles based on data for full-term babies, which my son wasn't. And that if you were going to give me percentiles that are meaningful, you would need to report them to me relative to a curve compared to other babies born 2 months early. And they all kind of admit, yeah, you're absolutely right. And in my head, I'm thinking, so stop freaking people out that don't understand this. Stop reporting these meaningless numbers. Got it? Okay. All right. Go ahead and turn the page. Okay. This is your time to complete 2.21. Again, if you're not able to finish it in the 5 minutes I'm giving you, don't freak out. Don't stress out. Just get as far as you can and work together. Go. So I am perfectly happy to explain any part of this, but I'm going to lean on you all to ask me if you'd like me to explain. So with the first one, you should have a z-score of -1/4, and that gets you not quite half of the curve. With the next question, I took advantage of the fact that I already have the z-score for 60, and I only bothered calculating the z-score for 73. Because I already have the z-score for 60 in the previous question. Why do I need to repeat those mathematics? Okay. And I just did normal CDF from -0.25 to +1.375. Okay, now, by the way, if you were using the pink paper to do this, what you would have to do is you would have to look up this z-score to get all the area under that, and you would have to look up this z-score to get all the area under this, and because you want the area between the two, you subtract the smaller one from the bigger one. Does that make sense? So you look it up and you find, oh, well, this is about 40% under, and this is about 91% under. Okay. So if you look up -0.25, you'll find it's at about the 40th percentile marker. If you look up +1.375, you'll find it's about at the 91st percentile marker. And since you want the area between the two, you subtract 40 from 91, and you find out the area between them is about 51%. Okay. Again, I went through that very quickly, so please do not shy away from asking me to explain any part of that in greater detail. Questions? Okay, so one question I was asked was to show this in the graphing calculator. So if I was going to do it in one step, first of all, I jump to the catalog. That's second 0. I jump to the ends by hitting the log button, and I'm going to select normal CDF. Now I'm going to show this 2 different ways. I can start at the lower z-score and go up to the higher z-score, and that is a way of it just immediately getting the answer. That's the area between the 2 markers. But to sort of use the calculator to emulate what you're doing with the pink paper, when you look up the z-score of -0.25, you're essentially finding this. You're finding everything under -2.25. And when you look up the z-score of 1.375 in the pink paper, this is what you're essentially looking up, everything under 1.375. So then what you do is you say, all right, well, this is what's under 1.375, and this is what's under negative 0.25, so this must be the amount that's between them. Okay, good. Questions? Now we're going to learn the first new skill of the day, and then I'm going to kind of walk you through a problem. We may or may not have time for you to try a problem yourselves. We'll see. So 2.22 says convert each given percentile to its corresponding z-scores. Essentially, this is working the z-chart backwards. I like to describe this as sort of a very annoying Where's Waldo search. Because if I ask you, if a value lies at the 3.92 percentile, what's the z-score? Well, yes, there's a calculator command for this, but you can also work the pink paper backwards, okay? And I'm going to model both. So option number one, you use what's referred to as the inverse norm command. Okay, so if you go to the calculator, go to the catalog, jump to the i's, which means you can hit X squared key, that jumps you to the i's. Then you do admittedly have to scan down a little bit to get to it, but you want the inverse norm command. We will eventually use the inverse t command, but that's something for second semester. Inverse norm. Now, I will warn you, people constantly get the normal CDF command and the inverse norm command confused. So I want to try to make this very clear. If you have the z-score and what you don't have is the percentile, you use normal CDF. You say, well, this is my z-score. What's the percentage under me or between these markers or over me or whatever? So if you have the z-score, you use normal CDF. It's normal to have the z-score. But if you're given the percentile, 0.0392, well, then you don't have the z-score. What you have is about 3. I'm standing somewhere that puts about 3% of the population under me. Where do I need to be? That's, you don't have the z-score, you have the percentile, and that's what the inverse norm command is for. So I'm just going to type the number 0.0392 into my calculator. And what you're now saying to the calculator is, on a normal curve, I want to be standing so that 3.92% is under me. Where do I need to be? And the calculator is going to say, oh, just be 1.76 standard deviations below expected. That's what the calculator is going to tell you. Okay? Now, if you truly understand this, then you can, even though I only just showed you this command, every one of you could tell me what this is going to be. Here's what I'm asking the calculator. If I'm standing on a normal curve and 50% of the population is under me, where am I? Where would you be standing? Where? At 0. You're standing at the mean. So it's going to say, oh, your z-score, it's 0 because you're standing on the mean. You are the mean. You're 0 standard deviations away from the mean. Okay? So this first number is negative 1.76. Now, by the way, for those of you who prefer the pink paper, this is why I say it's kind of like, admittedly, an annoying Where's Waldo search. What I have to do with this pink paper is I have to find 0.0392. That's what I have to do. And sometimes you can't even find the exact number. You just have to find something close to it. So if I go to my pink paper, I can find 0.0392 right here. There it is, 0.0392. You don't always get the exact number, okay? And then what you realize is, oh, in order to have that amount under me, I have to be at negative 1.76 standard deviations below the mean. Does that make sense? So you can use the pink paper to do this. I'm going to model one more, and then I'm going to ask you all to do the rest yourselves, because this is a very critical skill that you need to have. Okay, I'm going to jump to the very bottom one. I'm going to go out of order on purpose. If a value lies at the 99.83 percentile, its z-score must be. Now, by the way, you should already know, if you're above the 50th percentile, what better be true about your z-score? That's a question for the whole room, folks. If it's positive, exactly. If your percentile is above 50%, your z-score better be positive. So 99.83. I'll start by doing the annoying Where's Waldo search. I'm looking for 99.83. I see 84, 85, 83. There we go. So the pink paper is telling me if I want 99.83 under me, I have to stand 2.93 standard deviations above expected. 2.93. So I go back, and all right, if that's how much of the population you're beating on a normal curve, you're 2.93 standard deviations above expected. And I could have used the inverse norm command and just typed, I want 99.83% of the population over me. And it'll say, well, in this case, 2.929, which would round to the pink paper. Remember, the pink paper is limited to 2 decimal places. Okay? Take a minute to get the other 3 yourselves. I'll be generous. I'll call it 2 minutes for anyone who might be using the pink paper. So while you all are working, I once again revealed sort of a color coding system. One other thing I'd like to point out, and I did this on purpose, the percentiles I was asking you to find slowly step up in value. So when you look at your z-scores, they should flow from more negative to more positive, because we went from 3rd percentile to the 27th percentile to the 46th percentile to the 96th percentile, and then finally the 99th percentile. We kind of slowly migrated down the curve. Does that make sense? Or rather up the curve. Okay, does anyone want me to explain any of those z-scores? Okay, so this is the new skill for today. Okay, can you take a percentile and work it the opposite direction and figure out what z-score must have led to that percentile? And now I'm going to show you an example of where you would be expected to be able to apply this. Okay, and I'm going to say, based on time, this will be the last thing we do today. Okay, we'll start with a problem for you all to try yourselves tomorrow. All right, so here's an example of using this new skill. Continuing to use the same normal curve of 62,8 for heights of high school students. So same curve we were using earlier a moment ago. You're being asked to find the 25th percentile and explain it in context. Well, now you have 2 ways of finding the z-score associated with the 25th percentile. The bottom line is you want to find, where do I need to be so that I'm standing above 25% of the population? Now, I just gave you the answer, but it's important that you understand how to get that answer. Okay, if you go to your pink paper and you search for the 25th percentile marker, you're actually not going to find exactly 25%. You can find, when I see it, 2 numbers that sort of equally surround 25%. Does that make sense? I will tell you now that I don't care, and the folks that grade the AP exam don't care which of those values you want to go with. We understand the limitations of the pink paper. So we're just interested in you going with negative 0.6 and then either 7 or 8. I really don't care. If you want to call it negative 0.67 or negative 0.68, I instantly know this is a student who is relying on the pink paper, and that's fine. Okay. However, with your graphing calculator, you can get the more precise value by typing inverse norm of 0.25. And the calculator is now telling you, okay, if you want to be at the 25th percentile, you have to be 0.67 standard deviations below the mean. So find that. Start at the mean of 62 and subtract not 1 whole standard deviation. Okay, let's be clear. Standard deviation is 8 inches. So you don't do this. I'm going to subtract 1 of those. No, that's 1 full standard deviation below expected. I also don't want to subtract 2 of those. Now, I might want to subtract 2 of those if I'm being asked about low outliers. You know, how short do you have to be considered unusually short? Less than 46 inches. Okay, but in this case, we want to be 0.674 standard deviations below expected. Okay, and again, I'm just taking 0.674 because that's what the inverse norm command gave me. If you use 0.67 or 0.68, no problem. Okay, but that is the height that would be, okay, if you're this tall, we expect you to be taller than about 25% of your peers. That is what Q1 represents, and what I just said is what it means in context. We would expect 25% of high school students to be shorter than 56.608 inches. The very next question asks us to basically repeat what we just did, minus the explanation and context, but find the 75th percentile. So in the calculator, I would just type inverse norm of 0.75. However, for those of you in the room who understand and appreciate the word normal means both unimodal and symmetric, you should be able to tell me what the z-score is going to be without me having to hit enter. What would it be? Positive 0.674. Okay. If you are 25% away in the low end, well, that's the same thing as being 25% away in the high end. Put it to you another way. If you stand 0.67 standard deviations below, 25% is under you. Well, then it stands to reason if you stand 0.67 above, only 25% is above you. Okay, in other words, you're at the 75th percentile marker. So we repeat the exact same thing we did before, except instead of subtracting, you're now adding. And there's nothing in this question that said you have to explain yourself. Now, if we wanted to use our previous two answers to find the interquartile range, remember this is nothing more than Q3 minus Q1. Okay, so it's your answer from B, subtract your answer from A, boom, you're done. Make sure you put the inches. That's a good way of protecting yourself with context. And if you were asked to explain it in context, you might say what's in green. The range of the middle 50% of high school student heights is about 10.784. Or you could say the middle 50% of high school students seem to have heights somewhere between 56.6 and 67.3. Now we're going to end on a challenge question here. Can you find a method for finding the interquartile range which does not require first finding Q1 and Q3? This is not an easy question. It's me just being a math nerd. Okay. Can anyone tell me how could you get this number without ever getting either of those actual numbers? Anyone have any idea? Here's the bottom line for part D. And it absolutely involves the z-scores, but I wouldn't even use any of the fancy calculator commands, even though they can do it for you. Here's the idea. If I'm standing in the mean, Q1 is down there somewhere, Q3 is up there somewhere, and the distance between them is the interquartile range. Does that make sense? Well, what I'm arguing is I don't need to know this lower marker is 56 inches and this higher marker is 67 inches. All I need to know is Q1 is 0.67 standard deviations that way, and Q3 is 0.67 standard deviations that way. So the distance between them is 0.67 standard deviations plus 0.67 standard deviations. In other words, if you just say, well, what is this? That is how far in inches you have to travel down to get to Q1. It's also how far in inches you have to travel up to get to Q3. So the distance between them is just double that number. Does that make sense? And I never once had to actually calculate Q1 or Q3. I just took advantage of the fact that I know how far apart they are in terms of standard deviations. They're 2 times 0.674 standard deviations apart, and a standard deviation is 8. So multiply those numbers together, and voila, you've got your interquartile range. All right, folks. Tomorrow we will start with an example very similar to this, where you're given the percentile and you need to work backwards to get z-scores. With that being said, we're done for the day. Thanks for watching. Have a good one.